Let me hit this button. Okay, now, here we go. This chapter is going to be all about categorical variables as opposed to quantitative variables like means and proportions. Remember, a categorical variable, instead of having our data sorted as specific numbers, that's quantitative, right? Using quantities. Categorical sorts them into categories. And so the first one we're looking at is looking at colors of a bag of M&Ms. And normally we would actually do an activity like this and actually carry out the test that we're looking at with actual data. But since I'm trying to stay away from having food in here, we're not going to do that this year.
I ate a bag of M&Ms last night.
So,
should have told me about this beforehand.
The claim by the company. The claim by the company is that brown and red are 13%, yellow is 14%, green is 16%, orange is 20%, and blue is 24%. So, those are our claims.
Does it really add up to 100?
Yeah.
What does it?
13 and 13 and 14 and 16 and 20 and 24. That does.
It does not.
50, 60,
27.
7. No,
Something
there's no
with a
way.
7 at the end.
No, yeah.
Yeah.
Oh.
Okay, see, like, I'm not an idiot, guys.
Wait a
Thanks,
It's
Aiden.
all 13% of each brown.
Wait.
Yeah, maybe 7.
Oh.
These are both 13.
I'm so smart.
Okay. All right. On board? All right, we're on board. So, this is our claim. So let's take specifically the percentage of blues. And so let's say we took a sample, and here's the sample that we got on this table. Remember, these are categorical variables because instead of talking about percentages or means, we are instead keeping track of the color. That's a categorical variable. And what we're going to do is we're going to do hypothesis tests with these categorical variables. Now, if we were to do this with quantitative variables, what we would need to do to test this claim about the color distribution is we could start with blue and let P equal the proportion of blues. And we know our P hat, our sample proportion, would be 0.15. And our claim was that the proportion was 0.24. So we do the null hypothesis being 0.24. The alternative is that P is not 0.24. And we would do the hypothesis test for that. We would go through the 4-step process. We'd make sure, like we'd have our n times P and our n times 1 minus P for the null hypothesis. We'd go through the 4-step process and test and come to a conclusion about whether the proportion of blues is what they claim it is. And then we do the same thing for the proportion of oranges. And we do another hypothesis test, and we get another p-value out. And we do the same thing for greens. And we do the same thing for yellows. And we do the same thing for reds. And we do the same thing for browns. We'd have 6 different hypothesis tests, all giving different p-values. And that would tell us whether the distribution is what it's supposed to be. Or we could have one hypothesis test that will give us the information about the entire distribution instead of just one at a time. Right? Because if we were to do this out the long way, we would have to do each of these individually and have 6 different 4-step problems that we would do for all of these. So, this is a new hypothesis test that's going to use a new type of distribution. it would be pretty inefficient to do that. So we are going to have a different hypothesis test. This is called, this hypothesis test is going to be called a chi-squared goodness of fit test. This is chi-squared is, chi is a Greek letter, and it looks kind of like a fancy X. And then we're going to put a squared on it. So you'll see this written out. It means chi-square. And chi-square is a different distribution, is a different type of distribution, just like t was a little bit of a different distribution. And we had to talk about t-scores instead of z-scores. Now our test statistic is going to be chi-squared. And so our null hypothesis, remember, our null hypothesis is a statement of equality, or no difference, or no change. So in the context of this problem, our null hypothesis is that there hasn't been a change from the distribution from what the company claims. So in other words, our null hypothesis is that the company's stated color distribution is correct. In other words, the proportions are what we say they are. And then the alternative is going to be that that distribution may be wrong. And we're going to state that as saying the color distribution for them is not correct. We're going to say that as at least one of the proportions is not accurate. Right? That would be the opposite of my null. The opposite of it being the same is at least one of them is not right. So our here we go. Our null and alternative are going to look more similar to this. So our null hypothesis is saying that these proportions are correct. And we are defining P to be the proportion of the M&Ms that are that color. So here's what the claim was that here were the distribution for each of the colors. That's the null hypothesis. And then the alternative is that at least one of these proportions is not correct. And the way that we are going to test this is to compare something called observed counts with something called expected counts. So the observed counts, this is kind of like when we did scatter plots and residuals, and we had this formula of observed minus predicted. It's pretty similar in this case as well. Observed, just like when we did scatter plots, observed is the values we observed, is the values that we actually, the data points that we actually get out in the sample. That is as opposed to expected. Expected counts are what we would expect from the null hypothesis being true. So we'll take a look at how to get those expected counts in just a moment here. Oh, sorry. This is just, it's a common math thing that we use like I for an index to like mark something. So like, so question being, what is this I? Another place you might have seen it in this class is in the mean formula. When we add x sub I over n, over our sample size. And so this index says take each of these like individual values. It's a shorthand instead of writing out you know, blue, orange, green, yellow, red, brown. This I says go through each of those, cycle through each of those individually. And so this says start with x sub 1, the first value, and then go to x sub 2, and x sub 3, x sub 4, x sub 5, all the way up to x sub however many there are. So that's another place that you might have seen that sub I. Another place you might have seen it is when you did in sequences or a series in algebra 2 and tried to think about like what the next term in the sequence is. That's another place you might have seen that sub I. But let me go back to the table in our M&Ms. This table that was on this slide here, this is our observed. These are our observed values. This is the data that we got from our sample. To get our expected, values come from these proportions. For example, if we have orange, we are expecting 20% of all the candies to be orange. So all of the candies, there were 60 in our sample. So we had 20% of them that we're expecting to be orange. That means how many? 12. Right, 20% of 60. Or 0.2 times 60. That's why it says here that in general, expected counts can be obtained by multiplying the proportion in each category by the sample size. (24% of all the blues are supposed to be there. So for blues, we take 0.24 times 60 to equal 14.4. And that's what we would expect. That's how many of them we would expect to be blue. So I'll give you a minute and see if you can use those proportions and get the rest of the expected counts. Just like all the percentages we just discussed should have added up to 100%, the total expected count should also add up to 60. And what we're eventually going to do is we're going to compare what we observe with what we expected to get in some way, and that's what's going to give us our p-value. That's basically what's going to be involved in our formula.
So this is the expected. What does the p hat give you that we did over here? What is this then? Is this the observed?
That would be like a p-hat of an observed, yes. We're not going to use it because this is showing, here's what we would do the long way. So we're saying we could do this out the long way and do this 6 times.
Right.
Or use these observed and expected things that we're about to do.
So then why did they give us these and they don't match up with these?
Because these are what we expect if the null hypothesis is true. And remember that our null hypothesis doesn't always match up with what we get from our sample.
Okay.
That's why we have to compute a p-value, because our p-value is saying what's the probability of getting this sample with our null hypothesis being what it is. Should add up to 60. All the expected counts should add up to 60. 30 more seconds. Then I'll show what they are. Remember, for each of them, you are taking the 60 and multiplying by what the null hypothesis says the proportion is. And doing that down the line. That means that since the null hypothesis claims that there are an equal amount of red and brown, they're both 13%, your expected amount for those two should be the same. There they are. So here's a new table, which has the observed and the expected being side by side. And what you should notice here is that this distribution doesn't look very similar to what I would expect. Some of them are pretty close, like green is pretty close to what we would expect, but yellow is pretty far off. Blue is also pretty far off. And then we're going to have a table that gives the observed and the expected as well. And our question is, how far off are we willing to go? How far off are we willing to be? And the answer to that is going to be basically the one formula you're going to need the whole chapter. There's one other thing that I guess you can consider a formula if you wanted to, but this next slide is going to have the big formula on it.
Watch me still have trouble memorizing.
It's on the formula sheet.
Yeah, watch me still have trouble memorizing.
All right.
Can we have a day, like, later on when we're doing a review, where we go over the formula sheet, please? I know that sounds really weird, but sometimes it confuses me more. Just an idea.
I can take 10 minutes one day and take you through it.
Your sheet of paper that you always write is so helpful. Oh, thanks. It writes it down in words that I understand.
Yup, agreed.
Like it says, this is the formula for this. Boom. Thanks, guys. I use it to do my homework for the writing test.
All right. We are going to, hopefully it should make sense that in some way this calculation is going to involve comparing your observed values with what you would expect the values to be. In a similar way that we would look at this bar chart and compare it. But this formula is going to scale it down to how far off, based on our sample size and based on what our expected values actually are. There's the formula. It is the sum of observed minus expected squared, all squared, over expected. That is going to be your formula, your one big formula that we're going to use the whole chapter. So, there's the formula again. Let's walk through this. Since there are, we are adding together 6 different terms, one for each color. So I'm going to take you through the first one, and then you're going to do all the rest of them. And this is the one time that I'm going to have you add all of them together and calculate it out by hand. Quickly. So This is going to be the one time where I'm going to have you add them all up and do the formula out by hand. And then the calculator is going to do it for you. And you'll do like formula, plug in the numbers, answer. So for blue, I'm just going to show the one for blue. And then I'm going to have you try the rest. Observed minus expected squared over expected. There we go. Observed minus expected squared over expected. Here's our observed for blue. Our observed for blue is 9. Our expected is 14.4. Squared all over expected. Our expected is 14.4. So there is our first component. And this is a summation, which means we are going to add together the next term. You're going to do the same thing for orange, and then you're going to do the same thing for green, same thing for yellow, same thing for red, same thing for brown. Add all of the pieces up together, and that will give you the entire statistic. So take a couple minutes and do that. You should get about 10.18 as your answer. You should get about 10.18 as your answer if you're doing it correctly.
And we do that for each color?
You're going to do that for each color.
Because you need to find the chi-square statistic.
It's a summation.
Okay.
So we've done the first term of the sum. Write out the other terms.